Happy Sunday. This is PFG Live, the podcast dedicated to the writings of internet philosopher. Hey man, why didn't you? Hey man, why didn't you use the shaper? Welcome aboard. We got a good crowd in Discord and folks are showing up on the YouTubes. Let's see. We've got who reported first? Bill Olney from Rome, New York says it's 36 degrees Frankenstein and cloudy in Rome, New York. DBX says at the White Plains of New York airport. Let's see. It's winds are 300 at 10, visibility 10 miles, few clouds at 3,000, broken 11,000, temperature 07, dew point -04, altimeter 2971. Evils in Ghent, Belgium says that it's about 20 degrees, and if you could read this, you need a better job. Josh says in tropical Winterpeg, reporting winds are 190 at 10 knots, visibility 15 statute miles, overcast at 4,300, -5, dew point -6, altimeter 2992. Dale in America's Attic says it's 1 degree science and cloudy. Welcome aboard, sir. Warren Jones in Sutton, New Hampshire reports 36 degrees Frankenstein, partly cloudy and calm winds. Over on the YouTube side, we have CS Weldfab, who says 37 degrees, sunny with the occasional flurry in East Tennessee. Hello, everyone. Welcome aboard, sir. Carl Tauber says it's 42 degrees and cloudy in the People's Republic of Rhode Island. Welcome aboard. Unix Carbide in the Brooklyn of New York says it's 48 degrees Fahrenheit and nice. Oh, lovely. Tucker in Tuck's Garage says it's 31 degrees Fahrenheit and snowing in Buffalo, New York, which is basically the normal condition for Buffalo, New York. Orjan, welcome aboard from Trondheim, Norway. He says it's -10 C. Leave me alone. No, he didn't say that. -10 C. Adam at Langerman Machine says in Bristol, and he's in Bristol, Rhode Island. Humidity 79%, wind speed west at 6 miles an hour, barometer 2968, dew point 36 degree Frankenstein, that's 2 degrees Celsius, visibility 10 miles, wind chill 38 Frankenstein. Oh, Test Room 2003 showed up. Welcome aboard, sir. He says, good evening from Oostkapelle, Netherlands, 2 degrees science and 82% relative humidity. Dave G says 30 Frankenstein, cloudy, Northwest Ohio. Side note, PFG Stone video just posted, and thanks. Awesome. I will look for it. That sounds fun. Ted Hyde from Eustis, Florida says nearby at Kilo Lima Echo Echo, it's 340 at 10, gusting 18 knots, 10-mile visibility, scattered clouds 1,400, broken at 2,200, overcast at 7,000, temperature 21, dew point 16, altimeter 3015. Remarks 404 not found. Story of my life. I got y'all. I got everybody. Somebody's going to come in at the last minute. Welcome aboard. It's a wonderful Sunday. Here in the Windham, New Hampshire, it is 41 degrees Fahrenheit, 79% relative humidity. Winds are northwest at 6 miles an hour. And it's kind of neat. Everything seems to be melting. And that's good. We could use a little melting. So welcome aboard. Man, we got people pouring in the chat in YouTube. Manchester Airport's reporting winds are 310 at 8. Visibility 10 miles, broken 3,500, broken 11,000. Temperature 07, dew point -01, altimeter 2963. So Dave, maybe if you get a chance, shoot me that link on DM for your video. I want to see it. Harvey Newman, welcome aboard. He says hello from Santa Rosa, California, where it is sunny and 51 degrees Fahrenheit. That is awesome. So we had a good week. I took some time off yesterday, which means I didn't work in the shop all Saturday, which was very unusual, and I kind of liked it. I needed a little bit of a reset. More good experiences with DHL. orders shipped out the door, across the pond, into the unknown, and we'll get a report on them when they arrive. We do have one community item.
We interrupt our program to bring you this important message.
So we got a report from Sutton, New Hampshire, that the brown packing material that McMaster Carr uses is flammable. Please, if you are welding, do not surround yourself with McMaster Carr packing material. That is all. Okay, that's that came in this morning, and I thought that was important enough to interrupt everything. Today's topics were triggered. I was personally triggered by a couple of events. The first event was an offshoot of us getting involved with this Meshtastic radio fun that we've been having, and in fact, I'm currently working on a project to put a new node somewhere in Boston, and that should be fun. So I 3D printed a bracket for the so-called Wismesh Repeater Mini. That's $107 right there. Very inexpensive to get involved. That thing serves up Bluetooth Low Energy to do it programming and access, and then it, of course, does its magic on the Meshtastic network at 900 megahertz. So that's going somewhere in Boston real soon. But what that did is that caused me to start thinking about things. And then Unix Carbide has been very active in playing with the Meshtastic nodes, and now Paul Morley is getting active playing with them, and we're having some fun. But for an installation in a busy place, busy meaning electromagnetically busy, right, and full of radio waves, which is pretty much everywhere. But anything in a city is going to have a lot of RF signals flying around. And my concern was that these little processor boards with the integral radios for the LoRa, which is the 900 megahertz side, and BLE, which is 2.4 gigahertz, those little radios can get crushed by strong signals if they don't have a way to protect themselves. And I'm pretty sure that those inexpensive radios are not very robust like a good communications radio is going to be. So what I wanted to do is I wanted to put a filter in front of the radio. This is not, by the way, this is not worthy of a Nobel Prize. This is like everyday kind of stuff. I wanted to put a band pass filter in front of the LoRa radio, which would allow the 900 megahertz band, which is in the United States. It varies, by the way. In the United States, it's 902 to 928 megahertz. In Europe, it's around 868, and I don't remember the range. But in our case, 902 to 928. So I wanted to design a filter that would pass 902 to 928 with very, very little loss in both directions. And it would reject everything outside of that band. And this is commonly known as a band pass filter. There's a bunch of ways to do this. And in the thumbnail for today's live, there's a couple of examples of it. And we're going to talk about these things. I'm going to do a little show and tell. But from a precision machining, making, implementation point of view, you have to cross from theory and electromagnetics into hardware, and that's where this came up. Was these filters? So we're going to talk about this in a little more depth. I even have the actual items sitting right here that we could talk about them. And the second event that happened that triggered some of what we're going to talk about today is Unix Carbide here. Yeah, Unix, are you okay? Is everything okay? You stable? Is it? I just want to make sure before I bring up the next topic because I get concerned. We have an agreement. Just put the earplugs in. We have an agreement that that we don't talk about the M word, magnets, around Unix. So we have to be careful. We have a safe word that we use in the Discord server. It's cucumbers. So we talk. Yes, right. Dale brought it up. So we're going to be talking about cucumbers today. So Jared, my magnificent son, comes up and he's built some interesting projects. He's interested in keycaps and making keycaps and designing keycaps, and that 3D printing and resin printing. And now we're getting ready to machine some. That'll be another topic. But one of the people that he follows was making a keyboard, and he was using Hall effect sensors and magnets to sense the key position. And there's some cool things that kids these days are doing with that. Instead of a switch per key on a regular keyboard. And one of the things you get to do is you get to measure the actual key position as you press it, and that could be useful. It also doesn't have any mechanical thing to wear out. So he came up and he said, "Hey, Dad, we need to get some 4mm by 2mm N35 magnets." Now, I understood 4mm by 2mm, but I didn't understand the N35. And as it turns out, it has to do with the strength of the magnet. Well, we spend an hour looking for his specification because that's what this guy built and he wanted to copy it. And boy, howdy, did we get down the rabbit hole. So I will talk a little bit about that. Mr. Harvey Newman, welcome aboard, sir. He says, hello from Santa Rosa, California. Sunny 51. Mr. Machine Creations, welcome aboard. Am I late? Dude, we were all born late. Don't worry about it. He says it's 35 and partly cloudy in the high mountain desert in Idaho. As long as the onions and the potatoes are okay, we're happy. Nice to see you. So, yeah, I think we'll start today with the cucumbers and get that out of the way. So I brought some show and tell, and my relationship with close your ears, Unix. My relationship with magnets is interesting. I actually have a patent on a magnetometer, which I designed a while back. It was, interesting. I don't think it ever became commercially viable. And but it got my head into the whole topic of magnetics, magnetic materials, and how that stuff all works. And that was kind of fun. And then time passes, and one of the projects that popped up is I was working for a nonprofit organization many moons ago as the antenna guy. And I'll save that story for later. Sorry, that's a later story. I get a call from a company that says, "Hey, can you grind magnets?" And I'm like, yes, we can. So what they needed some very, very, very strong magnets with a very, very, very flat surface. And these were, we'll talk more about materials later, but these were neodymium, rare earth, very high strength magnets that were in various sizes up to and including 1 inch diameter by 1 inch long. And I am here to tell you that a neodymium magnet that is 1 inch in diameter and 1 inch long is a scary item. and they get bigger and they get scarier. So as a yeah, I know Unix says terrifying, but if you think one of them's terrifying, if you possess two of them, you better be really careful. And I know that there's YouTube videos of people smashing magnets together. I am not kidding, folks. This is a really scary thing to do. So use caution. But what I do have for show and tell is to show what one of these magnets looks like, and I'll show you the project that I did. And again, this was months and months back, but the neodymium magnets that we use a lot of, these little guys, these are 10 millimeter by 3 millimeter, also very strong for their size. But when they get up to 3/4 inch diameter, that's what I'm about to show you. And if it looks like I'm handling it very carefully, it's because I'm handling it very carefully. Come on, get out of there. There you go. All right, so there's a 3/4 inch diameter by, I think, 3/4 inch long neodymium magnet. This is one of the sizes that I was grinding for these guys. And if you stop paying attention for but a second, okay, and they smack into something, they chip because they're very ceramic-like. But this particular one is still a magnet, and it's very, very, very strong. Let me put this away before I do something I will regret. So in that particular project, by the way, this thing in its safety case just yanked these guys off the desk. So the first thing I did is I designed these safety cases and I 3D printed them, and they have enough volume around the magnet to keep it from getting too close to anything. Fun fact, how do you get rid of magnetic grinding swarf? Okay, interesting question, and it has a delightful answer. Let me address that. So in practice, what ended up happening is I used my favorite wheel, the 5SG wheel from Norton, and that's a ceramic hybrid wheel. And it did get a lot of schmutz in the wheel. The use of a NOS made by Kinetic Precision to focus the full flow coolant helped to keep the wheel clean, but it had the interesting property that if you got any of the material on the wheel, which of course you're grinding it, you're going to get the material on the wheel, it would pull more material on the wheel. So the wheel got pretty contaminated. The NOS helped a lot, and the material got withheld by the magnetic chuck pretty effectively. So it cleaned up pretty well. It was surprising because I was truly ready for a disaster, because that material, the neodymium, was really hard to tame as far as cleanup is concerned. But it got attracted to and stuck very well to the magnetic chuck, and then cleaning it off the magnetic chuck, while a pain in the neck, was not impossible. So that answers your question, I hope, as far as cleaning that stuff off. So Mr. Tim Beattie says he did research in graduate school, magnets to focus plasma for reactive ion etching. Started as plasma in a waveguide, so a really cool crossover. Chemistry was chlorine and bromine base, so toxic as well. That is awesome. You hit all of the important points. So Carl's all excited. He wants to analyze your chlorine and bromine chemistry. I want to look at the waveguide, and all three of us should go out for lunch. The first thing I did is I designed, and I know I've shown these before, but I'm going to show it real quick. I designed a fixture. And by the way, talking about materials today, I'm going to You see this pattern at the bottom of this thing? This is where it got gripped by the vise, and then it's just a big chunk of aluminum, and then a place to grab a collet at the top. So it's aluminum, and it's these non-magnetic, keep that word in mind, these non-magnetic 3/16 stainless bolts. And then we had a standard hole, which was, I believe, a 1-inch hole. And then I designed these collets. So here's a collet that it was 3D printed on the Form 4. Okay. Here's another collet that was turned on the on the lathe. I can't help but to get somebody upset.
Lathe tooling.
Yes. So this was made on the lathe, and these guys pop in to there, and now we can put our magnet in here, tighten it down. This is in a grinding vise, and life is good. So that's how we're able to hold these very, very, very strong magnets. So then, using an 8-inch wheel that was pretty new, I determined experimentally that the grinder spindle going over with the wheel going over it was sufficiently far away that nothing bad was happening. That was the second part. And then we started grinding. And the recipe, I figured out the recipe as we went. And I got some really good surfaces and measured the surfaces with, I know you're going to find this hard to believe, with an optical flat and a monochromatic light source. And we were getting very good flatness, which is what they wanted for their business application. So that was, here's another tool. Let's see. This was just a piece of steel, and this was used, I can't remember exactly. Oh, the steel with the electrical tape over it, I think was used to pick up a magnet that had gotten into the wrong place. While we're on this guy, let me tell you about materials. So this piece of aluminum happened to be not the aluminum you expected. This is 7050 aluminum, which a friend of mine who's in the aerospace business gave me a long time ago. So when I went to make this fixture, I said, what better thing to use than a piece of aluminum from the aerospace business? So this is 7050. You see these lines? That's corrosion. This stuff was very, very prone to being corroded by the stuff that was going on. So this is actual corrosion on the 7050 aluminum. And I later learned that the 7000 series of aluminum is very prone to this sort of stuff. But of course, in this application, it didn't matter. But it was just ugly. So that's how we held these magnets. And then eventually we got the job done. So I did a little research because Jared is saying to me, I need an N35. So it turns out that in the industry, they have a measurement for magnet strength. It's really a per material rating. And N35 was a lower strength magnet. It might have been the earlier magnets in the world of rare earth magnets. But I found a list. This is from Stanford Magnets, a company that makes and sells magnets. A list of the magnet types, and I did not know that there were so many types. So we have a neodymium iron boron, I have to translate, magnet. They don't give the strengths with this list. A samarium cobalt magnet, an aluminum nickel cobalt magnet. But wait, there's more. Oh, they do give the strengths. Here we go. A ferrite magnet, which, by the way, is the old school magnets before we saw common use of the rare earth magnets. And here's how they rate. I'm trying to see if they have, they rate them a bunch of different ways. 42. Yeah, I don't see the measurement that they were using for these N. Oh, there it is. So neodymium is generally regarded as an N42. Yeah, of course, I don't see an N35 on this list. The strongest one is the neodymium at 13,000 Gauss. Alinco, which is the aluminum, nickel, cobalt, is 12,500 Gauss. Ceramic, which is not really a very good, they call it ceramic 8. I don't know which one that is 3,850 Gauss. That might have been the ferrite. That sounds like the ferrite. Samarium cobalt, 11,000, and magnetic rubber, 2,000. Unsurprisingly, the weakest of them. That's the stuff that you've seen. It comes in adhesive strips, and those are the different magnets that these guys sell. So now I'm looking for this N35. Well, I will tell you that we could hardly find it. Every single thing we found was the N52 or unspecified, which was really not very helpful. Yes, Evils, good idea. So the numbers I gave, there is an energy product on the list there too. And that's not what I was giving you. I was giving you the max Gauss. Mr. Tim Beatty says aluminum nickel sounds like a really cool material. So Alinco magnets have been around a while, and they're nice and strong. Which of these magnets are dielectric and which are conductors? You ask hard questions. I don't know that we're going to go that deep today. Evil says, I hope you touch on magnets' maximum temperatures. Right. So we will talk about that. I just want to make sure. And we did a thing on magnets a while ago, but I'm going to give you my mental picture of how magnetic materials work. Okay. And then I notice I carefully said magnetic materials because there are materials which have magnetic properties but don't end up being permanent magnets, and then there are permanent magnets. So if you imagine a big piece of plywood with a bunch of nails, and those nails are going through those. So, Mr. Tim Beatty, if I say anything factually incorrect, your job is to jump on my case, okay? And I see your Cooper pairs. So we have a bunch of bar magnets, right, from third grade, and we have a nail going through each one of those bar magnets, and it is nailed to a board. And we have a random assortment of these magnets, and they are turned in a random assortment of ways. Okay? So that represents what your typical piece of iron would look like. Now we come along and we apply a magnetic field, like maybe we wrap a big coil around everything and we turn on a DC current. And what it's going to do is it's going to straighten out. Oh, I left out one thing. Sorry. Each one of the magnets has a rubber band going from the end of the magnet to the plywood. Okay. So big plywood sheet, random magnets, a nail for a hinge, and rubber bands going from the end of each magnet to a nail on the plywood. Is everybody with me? Does anybody have any questions? No, I'm not going to tell you what grade plywood it is. So if we just approach this thing and we maybe come along and we measure it with a magnet, an external magnet, we'll find out that it is magnetic, right? If we approach it with a magnet, some of the magnets might twist a little bit, but in general, it's going to be attractive to the magnet we're holding in our hands. Now, if the all the nails are too tight and all of those bar magnets can't rotate, it might not be magnetic because they might all cancel. Okay. So now if we come along with a big strong magnet to our sheet of plywood and we make a bunch of these magnets turn and then we take it away, if the rubber bands pull them all back, then we haven't changed the system. And we don't have a material which is a permanent magnet. Now we come along and we make all of our nails rusty. Okay? So now all of our joints are these horrible rusty hinges. Now we come along with a really strong magnet and they go, and they all the rusty hinges turn and all the magnets align, and then we walk away, but the rusty hinges don't let the magnets go back. So now if you show up with a piece of iron, it's going to be attracted to the system because now it has stored a so-called magnetic charge. So you'll hear these magnets on rusty hinges with rubber bands referred to as domains. So if you hear the word domains in the discussion of these magnetic materials, that's what they're talking about. So that's how magnets work. How do demagnetizers work? Demagnetizers go in with an AC waveform, big strong AC waveform, okay? So if you have one of these little demagnetizers, you know that there's this, it's like a transformer winding with a gap, and you plug it into the wall, so it's going 60 hertz, right? And you put something in it and it buzzes as you go across that gap. What it's doing is it's flipping the domains back and forth and back and forth and back and forth and back and forth, and then you slowly remove the field from the demagnetizer. By the way, that's important. You slowly remove it, and now it leaves all the magnets on the plywood in a random position, just like it was before, and it no longer has a quote magnetic charge. Okay, everybody have their plywood and their bar magnets and their rusty nails and their rubber bands all figured out? Okay, that's your model for how magnetic materials work. Now, if you have a magnetic material that is magnetic, I'm going to use some wishy-washy words before we get into it. Yeah, Dale says correctly, it's the same as an electric mag chuck on a grinder, which has a demag cycle, which mine does. So when you're done using the mag chuck, holding down your part, you turn it to the demag cycle, and this is exactly what it does. Different waveforms, different, details, but that's what it does. And then you just go pick up your part off the mag chuck. Okay? So that's your model for how these things work. And it's pretty simple, right? It's pretty simple. It's kind of simple. Okay, it's not simple. So that's a really good model to stick in your head, and it represents what we call ferromagnetism. And the reason the only flavor of magnetism you've heard about is ferromagnetism is because it's the strong one. It's the one that has to do with your fridge magnets, your grinding chuck, the magnets that may or may not hold a piece of electronics up against a public structure somewhere. All of these things operate with what we call ferromagnetism. Ferro, from the root of the word for iron, ferrous, right? And it's these big domains in the iron or the appropriate material that are on their rusty hinges on that big virtual piece of plywood. So I'm going to read you a little bit about ferromagnetism in detail. You can also have feral magnets. I think we have a feral magnet. It's our bird feeder, and all of the squirrels discovered it, and that's our feral magnet. So ferromagnetism is the strongest, most observable flavor of magnetism. It describes the induced magnetization of a material due to the presence of an external magnetic field Well, that's magnetic permeability in ferromagnetism. It is the most common magnetic property that you're aware of. It's an unusual property in that it only occurs in certain substances, and of course, iron is one of them. Nickel, cobalt, and alloys there too. And there's some rare earth. Of course, we get into the rare earth magnets, but it's all ferromagnetism. There are non-magnetic alloys, such as stainless steels, okay, which are composed of ferromagnetic materials, but it happens in such a way that the ferromagnetism is no longer a factor. It's weird, and that's material science. Yeah, we talked about that. I have to say this. I'm actually required to tell you the following. In 2009, a team of MIT physicists demonstrated that a lithium gas cooled to less than 1 Kelvin can exhibit ferromagnetism. This just in. Okay. So that's ferromagnetism, and that's the thing that you're used to seeing, and the thing that you deal with every day. It doesn't end there. And the last time we talked about magnets, I alluded to a couple of other things which are actually kind of fun. Two of these things lead to some good party tricks, so you're going to want to pay attention. And those two things are called paramagnetism and diamagnetism. So paramagnetism is also an attractive force with a magnetic field. So if you walk up to a material that has paramagnetic properties, and with any magnet, it will tend to be attracted to that magnet. So we say that these things have a magnetic permeability. Okay, that's the tendency to concentrate field lines, magnetic field lines, greater than 1. So greater than a relative permeability of 1. So what are some examples of materials that are paramagnetic? Okay, Unix, take the earplugs out. You need to hear this. Materials that exhibit a paramagnetic attraction. Okay, he's listening. Platinum, tungsten, cesium, aluminum, magnesium, lithium, and sodium. Those are just some examples. So we joke about how aluminum, magnetic aluminum. Aluminum is in fact paramagnetic. And Unix, you and I are going to have to put together a little demo of this and show this effect. And it's real. Yes, you got to keep up with your low sodium diet. So does it care that it's not ferromagnetic? So it's not about north poles or south poles. It's about a magnet attracting aluminum. Now, this is so weak that you are unlikely to see the effect unless you specifically go to set up an experiment to observe it. But I think it's really cool. The next one is even more interesting. So that's this is the second kind of magnetism, paramagnetism, okay? Paramagnetism is attractive. I got to take a sip of my Go juice. Okay. The next one is called diamagnetism. Okay? Speaking of your diet, diamagnetism. These are materials that have a relative permeability of less than 1. And they will repel a magnetic field. And interestingly, diamagnetism was discovered in 1778. And what it does is it repels, it is repulsed by a magnetic field. Also, very, 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 Dale says Unix Carbide is going to need a strong drink to make it through this podcast. He's okay. We talked about it. He was, He's taking the vitamin C, if you know what I'm saying. So anybody want to guess a material that is diamagnetic? No, if you have a PhD, you're not allowed to vote. Does anybody want to guess a material that is repelled by a magnet? I'm going to wait for a couple more guesses before I rule on Dale's guess. Josh? Another magnet? No, this is not part of it. Yes, you are repelled by a magnet. So Dale was correct. Water. Water is actually measurably and demonstrably at a bar repelled by magnetic. So the top one is any superconductor, okay, is repelled by magnet. You've seen superconductor levitation. Pyrolytic carbon, bismuth is really high up on the list, by the way. Neon, mercury, gold, silver, carbon, lead, copper, and water are all diamagnetic. So I was at a training course for a bunch of folks that were customers of the company I was working for, making surveillance devices. I won't get into details, but one of the guys was just hysterical. He was a senior technician. He was a cool dude, very smart, and we're literally at the bar in this resort, and he pulls out a thing, and he gets this cork, right? Just a cork from like a wine bottle, a needle. Okay, so sticks a needle in the cork, so there's a pokey bit sticking out. He takes a straw, these stirrers that they have at bars. I don't go to bars a lot, but he took one of those stir sticks, those little plastic ones. He grabbed a cherry tomato. Okay, 2 cherry tomatoes out of the thing, and made it like a dumbbell, a whiskey compass, kinda. So now he put them on either side of the stick, and then he very carefully balanced it. So now you have this. It looks like a compass, right? You have this stirring stick on a needle with 2 cherry tomatoes, and then he pulls out this cylindrical thing in his hand. I didn't know what it was, and he approaches one of the tomatoes, and it starts turning. And he approaches the other tomato, and it starts turning back. And I'm like, what is this science? And he opens his hand, and it is a stack. It had to be a 4-inch stack of, I'm guessing it was a 1-inch diameter neodymium magnets. It was more than one magnet, and it looked like a roll of nickels, and I think he had tape wrapped around it, which now scares the heck out of me. So it was a very strong magnet and some very delicious looking cherry tomatoes. And he demonstrated to me this concept of diamagnetism at a bar. You thought I was kidding. So if you guys want to try this, all you need is a couple of cherry tomatoes, a needle sticking out of a cork, and a strong magnet. And you've got a way to convince yourself about that. I thought that was it. I thought I knew everything there was to know about magnetics. And then, any guesses what's coming up next, Mr. Tim Beattie? Any guesses? What's the next magnetic effect? You could do it. Unix, you want to guess? One day we'll have to tell you the story about why Unix has a magnetophobia. Okay, the next one, I'm going to take a sip while you guys type. Yeah, Unix says the punchline to that whole story is hard drives. Which, by the way, hard drives figure into the very next effect. So there are 2 more remaining. And the first one is called ferrimagnetism, Ferri, ferrimagnetism. Ferrimagnetism is where a bunch of the domains point one way, and then the other half of the domains point the other way, but not as strong. Why this is important, I'm not sure, but here's the line that caught my attention. It was discovered in 1948, and since the discovery, and magnetite, which, by the way, was the first magnetic thing humans interacted with, right, to make compasses. Magnetite is actually ferrimagnetic. Since the discovery, numerous uses have been found for ferrimagnetic materials, such as hard drive platters and biomedical applications. And then, in case you didn't have enough to do tonight, when the material is amorphous, that means no crystalline structure, one talks of sperimagnetism, S-P-E-R-I, sperimagnet. We're not going there. Don't worry. Don't panic. And we talked about magnetite, and also some of you might have heard about yttrium iron garnet, YIG, which is used in electronics. It's a very interesting material. Okay, I have one more left on my list. You'll never guess what it is. It's called, I don't make this up. It's called antiferromagnetism. So I'm not even going to explain it. Antiferromagnetism is where the domains point opposite. Half the domains point one way, half the domains point the other way, and they're all the same strength. Why that's important, I literally have no idea. So now I want to show you. I got a present from one of my good friends who I can't identify. Just trust me, he's a good guy. And he sends me this thing, which was heading for a dumpster, okay? And he saved it for me. And I opened it up. By the way, this has been here for a while. And it is a permeability indicator. Okay, there it is. Permeability indicator from Severn Engineering Company, Annapolis, Maryland. And I thought that was a model number there, 4292. I have a funny feeling that's a serial number. And what this is, if you're on video, you get a little treat today. It looks like a balance beam, okay, is a weight on one end. And it's very carefully balanced. And on the other end of this arm, it's holding what I believe is a magnet. Okay. And on top is a little screw-in thing, which I finally figured out was a standard material sample. Okay. And there's a standard material right there. And the material is labeled for 2.5 mu. So that's an indicator of its permeability. And what it is, it's making a differential measurement between the material above the magnet and then the material that you're going to hold it up to. And then it has to, if it has enough force to pull down on this magnet, and the force is set by this counterweight, then you can determine if it has a permeability higher or lower than the number on the sample. Now, this is the lowest sample I have, is 1.05 mu, and I figured out why it's important. So I'm going to do a quick demo for you of the Severn permeability indicator. Okay, we'll start with something obvious. Okay, piece of 4140 steel. So we usually talk about permeability in terms of relative permeability. Permeability is denoted by the mu symbol, and if it's a mu sub 0 or naught, we call it mu naught. Mu naught is the permeability of vacuum. So it's the support for magnetic fields in vacuum. So if you have something that's got a mu that is 2 times that, we say that it has a relative mu of 2. It's twice as happy having magnetic fields in it. So you know that if you wave a magnet around, it doesn't feel any forces until it comes near something that it wants to stick to. So here's something it wants to stick to, a piece of 4140 steel. So watch what happens as I approach. I'm going to hold it closer to the camera. Whoops. Approach this 4140 steel. Boom. It's like, gimme. Okay. So we know that the 4140 steel has a permeability greater than 1.05. And I have another one. They go up to, I have 4 of them, and it goes all the way up to 2.5. So clearly this is set up for measuring very low permeability things. So let's take out a piece of brass. Okay. So here's a piece of brass, and I'm going to do the same experiment, right? Nothing going on. Okay. So brass, okay, has a very, very low permeability. Carl, we will talk about mu metal. Give me a minute. Okay, this is interesting. Here's a piece of aluminum. Okay. Now, aluminum, we already decided, is paramagnetic. Okay, we got nothing here. So aluminum doesn't show up on the scale. Here's a machined piece of 316 stainless. Okay, I know this is 316. It's not my part. It's from others. And we're going to try it with the 316 stainless. Nothing. Okay. Now, here's a part. Here's a bolt. This bolt is 18/8 stainless. I forgot to grab. Oh, actually, I have one here. Hang on. Yeah, we're doing it live, folks. So this is 18/8 stainless. Let's test it. Ready? Oh, it grabbed it. Okay, so this 18/8 stainless is magnetic, and it's got a relative permeability greater than 1.05. Interesting. Now, this one this one I hadn't tested. I know this is 316 stainless, and it's a bolt. Okay, let's see what happens. Bonk. It attracted it. Ready? One more time. It attracted it. So I hear what you're saying. You're saying, wait a minute, 316 stainless. So this is the bolt that I just showed you in that fixture that I built. And I bought these in 316 stainless because they were non-magnetic. And what we just proved is that they're a little magnetic. And we actually can measure that the permeability is slightly above, or maybe about equal to, 1.05 times mu naught. Isn't that crazy? So I want to say a big thank you for this magnificent tool from my friend. You know who you are. And this is the first time I've gotten to actually play with it and show you what it's for. Okay, so that's called magnetic permeability. Right. So the question is, why did I just show you 2 pieces of 316 stainless, and one showed a permeability of basically nothing, or a mu of 1, and the other showed a permeability of at least 1.05. Now, Dale, you can't answer this question, but can anybody guess why the bolt made out of 316 showed some permeability, but the part made out of 316 did not? Anybody? Evils is typing. Rolled threads. What about rolled threads? So the part that showed no response was the machined part. Heat treating, interesting question. Deformation, you're actually circling the right answer, Evils, but there's a specific word you need. So when the part gets formed, and bolts, as we know, are frequently roll formed and swaged, they get work hardened. You've heard the term work hardened. The crystal structure changes and it becomes magnetic. Not a lot magnetic, but we just demonstrated 316 stainless, which, because it's a bolt, was I'm going to call it work hardened, and it started exhibiting magnetic properties. Very interesting. And it's probably the little test set that I just showed you is probably to detect if that happened in stainless steel parts where they didn't want that to happen. Like, for example, around very, very, very high magnetic fields, or maybe electron beams, and you don't want anything to have a magnetic permeability. So that was very interesting. So we got to the end of magnets. You guys know everything you ever need to know about magnets. And we finally found some magnets to order for Jared that met his specifications. Actually, the size, he wanted the strength. We gave up on the size. So we ordered two kinds, a little bigger and a little smaller, and he's going to experiment with his project. And that got us to the end of Magnetville here. Okay. More than you ever wanted to know about magnets. We're going to get back to our filters now. So now we're playing with. Unix says it's definitely more than he ever wanted to know. We're not going to go for isolators right now, Mr. Tim Beattie. That is definitely crossing the streams. So there are applications in RF waveguides for using magnets to steer signals in waveguides, and I don't want to touch it because we'll head right off into the weeds. We're already overtime. Don't dump all your platinum stock, dude. Yeah, I know. Just it won't hurt you. I promise. The big platinum bar won't hurt you. So let's talk a little bit about making this filter. So what I did, and this is a couple of years ago, I started this project, and it was not for the 915 band. It was for some GPS stuff. I needed a filter for GPS, so I started studying filters and how to make them. And you'll see how this ties back to everything we've been talking about. These that are, I know I showed it to you in the thumbnail. These are called comb line filters, like combing your hair, comb line filters. And what it is each one of these bars is, you could think of it like an inductor, okay? And then at the top of it is a capacitor formed by this getting stuck through a little piece of a little ring of plastic, which you may or may not be able to see. Oh, there you go. You see the plastic? This side is soldered. We'll talk about that. This side's a piece of plastic, and then there's a pin that goes into each one of those, and it is adjustable. So the pin can be pulled in and out of the tube, which makes it an adjustable capacitor. So you have an inductor and a capacitor, and that makes a resonance. So for you audio guys, imagine a tuning fork, okay? This structure plus the capacitor that it made inside of here is basically the RF version of a tuning fork. So if you have a tuning fork, 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 and you excite one of them, they're going to excite each other until to get to the end, and then they take your signal out. So that's the short version of it. And then by adjusting these to very slightly different frequencies and adjusting the spacing between these, I'll call them tuning forks, okay, you get a filter, and you get the shape filter you want with a nice flat top and nice steep sides, and that's the magic. So when you go to your filter catalog, okay, these ones were made by K&L, and you buy this thing and it costs you $1,400. It's pay the man the $1,400. This was the design of these, the adjustment of these is very impressive. Let's get back to the shop. So we're in our shop and we're going to build one of these things. What do we notice? Does anybody notice from the color or the stains on this thing something interesting? I will tell you that the base metal here is aluminum. It is very, very much like a saw filter, Carl. Absolutely. It's silver plated. Yes, Evil's picked up on it. So these guys took a piece of aluminum, they machined it, and then they silver plated it. Why did they silver plate it? It turns out that we don't want in our filter here, in our RF filter, it has an RF connector there, an RF connector there. We don't want any loss through our filter. So in the frequencies that we care about, we want no loss. We can't have no loss. We want very little loss. So Carl is correct. Conductivity. So if there's any loss in the metal that the RF current is flowing through as it's bouncing around inside that filter, that loss, that resistivity is going to show up as a loss in our filter. So I start thinking about this and start thinking about how I'm going to build my version of this. And this gets us into something called skin effect. So skin effect is a very important concept in RF electrical engineering. And let's do another thought experiment. Let's grab a light bulb and a battery, okay? And we're going to hook the negative to one side of the light bulb and the positive to the other side of the light bulb, and we're going to light the light bulb up, and we have DC current flowing through this piece of wire. If we take a cross-section of this piece of wire and we ask the question, where is the current flowing down the wire, okay? Is it flowing the same in the center of the wire as it is at the outside of the wire? The answer is yes. This is a DC current flowing out of your battery, going to your light bulb, and the current is evenly distributed throughout the conductor. So it gets to use all of the conductor. So if you walked up to this piece of wire and you got out your very, very fancy ohm meter and you measured 0.0001 ohms, that's exactly what you can calculate is happening when you hook up your battery and your light bulb. Okay? Now, you get a different light bulb. You get a 120 volt light bulb and you're going to plug it into your wall. It's not running DC anymore. It's running 60 hertz. Okay? So that current is going back and forth 60 times a second. How does it affect the conductivity of that wire? Where does the current flow? Well, it turns out that as soon as it becomes an AC current in a cylindrical wire, the current starts moving out to the skin of the wire. Okay? And the center of the wire starts seeing less and less current. And you can calculate where 63% of your current is flowing from the surface down to 63%. That's called the skin effect or the skin depth. And the formula that you see on the screen here, that calculates the skin depth. Let me walk you through it. It's not really that scary. It says that the skin depth is equal to the square root of a ratio. The ratio is 2 times the resistivity divided by the frequency times mu, the permeability of the material. So it cares about the resistivity of the material, the permeability of the material, and the frequency you're operating it at. Interesting? So as I turn the frequency up, and instead of using 60 hertz, I'm going to use 60 kilohertz to light up my light bulb. All of a sudden, I increase the frequency by a factor of 1,000. And I'm going to decrease the skin depth by a factor of about the square root of 1,000, or about 30. Okay. What if instead I'm going to use an RF signal? Maybe my wire is actually an antenna. Oh my God. Okay. All of a sudden, we start using less and less of the conductor. And we can calculate how thick that conductor has to be to contain, for example, 99% of our current. Okay, so let's take a look at some of the data that I calculated for you. If we use a piece of, let's say, aluminum, and we operate it at 60 hertz, the skin depth is 0.4 inches. So if you have a big aluminum tube, and it's solid, and it's 4 inches in diameter, which is 10 skin depths, it's pretty much going to use the whole thing even at 60 hertz. Okay, big fat piece of aluminum. As I go up to, let's say, 1 megahertz, AM radio, that skin depth drops to 0.03 of an inch. Now, that's 63%, okay? So let's go 4 skin depths. That's a pretty good number. I think that gets you to 99%. So that's 0.12 of an inch. So if you have that nice 4-inch tube carrying your 1 megahertz current, once it gets to 0.12 of an inch from the top surface, you don't need the aluminum anymore. Now, you might need some more for mechanical structure, but the electrical's done. Wait, it gets better. If we go up with aluminum to 1 gigahertz, now your microwave oven in your kitchen operates at 2.4 gigahertz. So does your Wi-Fi, which, by the way, is why you can't watch the ball game while your kids are on making popcorn. So it's 1/10,000th of an inch, a tenth. So at 1 gigahertz on that tube, only a tenth is being used to carry the current. That's called skin effect. So when these guys are designing a filter that's operating at, let's call it 1 gigahertz, they know that in silver, it's also, by the way, it's about the same in silver. It's about a tenth. They know that all of the current flowing in this filter is happening in 1/10,000th of an inch. So they decided to plate it with silver and lower the loss. Now, I have some questions about that, but that's why they did it. Okay. All the rest of this material is for mechanical strength. Interestingly, stainless steel, which has a lot of resistivity, in order to get to make a good comparison, I'm going to drop back down to 1 megahertz. So if aluminum is 0.03 of an inch for 1 skin depth, copper is a teeny bit less, 2.6. Silver is 2.5. And stainless steel, that's 2.5 thousandths, and stainless steel is down at half a thousandth. Why? Because it's also very resistive. So remember, the resistivity of the material is in the equation. It's all part of the same deal. So stainless steel, you wouldn't use that anyway because of its lossiness. But all these materials have what's called a skin depth. And when you look at RF stuff, antennas, filters, you now know that maybe in a thousandth of an inch or two thousandths of an inch, that's where all the current's flowing. Now, if it's not a cylindrical shape that the current's flowing down, it gets interesting. But for all practical purposes, you could still use these numbers. So there's two things we want. We want our permeability. Well, we want our losses to be low. So 2 times the resistivity of the material is on top of that equation. We want that to be as low as possible, which is going to drive our skin depth smaller. But on the bottom, we have mu. So it says, hey, don't you want your permeability to be very high? What do we know about permeability? Well, iron has a high permeability, and if you run these equations with iron, it changes the skin depth a lot. But iron is very resistive, so it gets extremely interesting when you start doing the calculations. So that's called skin depth, and if you knew about resistance or resistivity or conductivity, it's all the same thing. Now you know about permeability, which is the magnetic property of how much the material was able to concentrate magnetic field lines. By the way, on the electric field side of things, the analog to permeability is permittivity. So stuff like Teflon, polyethylene, those have permittivities higher than air, and they like electric fields. They will concentrate electric fields, which we're not getting into today. So that is why, as I design and simulate these filters, I am thinking about how I'm going to make it, what materials I'm going to use, what shape do I have to make it to lower the loss and not negatively impact the RF performance? And it is a real interesting challenge. And I will tell you that you guys, most of you guys you deal with making stuff, okay? You deal with making stuff out of aluminum, making stuff out of steel, making stuff out of, copper, brass. This is, if you are making stuff for somebody in the world of RF, and communications or more exotic stuff, this is what they care about. So if they come to you and they say, give you some things that sound weird, it's okay. You could talk to them about it and ask them, is this for the skin effect? And they'll go, oh, it's pretty good. And that's why you might get requested to silver plate things and copper plate things, or make it out of copper. The stuff you love to machine is copper. Carl says, look at high voltage power lines. Each phase may have multiple conductors to do the skin effect. So that is true. And in fact, if you want to do some late night reading, Carl, look up Litz wire, L-I-T-Z, Litz wire. So Litz wire is a hack to use skin effect and try to improve a piece of wire by using many, many fine insulated wires and then weaving them in a certain way. It's called Litz wire, and it's a skin effect hack. It's also very expensive. Also, Carl brought up something called mu metal shielding. So mu metal shielding, I remember I gave a talk at the National Magnet Lab at MIT, and they had this room which was a shield room, and it was made out of mu metal. What's mu metal? Well, you know what mu is. Mu is permeability. It was a little room made out of sheets of this very high mu material. I remember that it didn't have a door. It just had a little hatchway that you went in, and it would reduce the magnetic field in that little room to almost zero, effectively zero. And they were using that because they were making measurements of the human electrical system. Okay. You know how you get an EKG and they put these electrodes on you? So they were doing magnetic measurements of the currents flowing in a human, and they would do it in this little chamber. And it was made of this stuff called mu metal. Let's analyze this now that we are super smart. Not new metal, mu metal. Come on. So what's the frequency? Well, the frequency is very low. So the skin depth is pretty high. Okay. So they were using, let's say they were using an 1/8 inch thick slab of these sheets of mu metal. They would prevent, the reason they had high mu is because they had such low frequency, and they wanted to compensate for it. What happens at the lower the frequencies, the harder it is to keep the magnetic field out. What about that door? Well, that door was small enough that it was effectively not there at the frequencies they cared about, which was near DC. That's why they didn't need a door. But what if we start cranking up the frequency? Okay, now the skin depth goes down, but that door matters. It was very interesting. But mu metal is a metal that has a very high mu, and it's very expensive, and it's used for magnetic shielding. And that's what Carl was talking about. Carl says the coil of my dead induction cooker was wound with Litz wire. Well, that's why it's dead. Yeah, Dave. I know. I can't go deeper. It'd be too much. Ted says, used to be popular in older phone cable, flat and coily, a pain to terminate aside from crimps. Most of the cotton or poly would burn away. Yeah, in old radios, very old radios where they wound coils, big coils, they used Litz wire to get the losses down. Okay. And there was some amazing workmanship that went into that. You don't see it very often. You know where I last saw Litz wire was in a Loran transmitter. So there was a company in the Boston vicinity that I visited. I don't think they're around anymore. Megawave, and they had they made big Loran transmitters. And if you don't know what Loran is, it's in the United States right now, it's pretty much dead. It was a 100 kilohertz transmitting system that they put up a number of these transmitters, and it was for navigation. And if you had a boat, I know Carl had a boat, Loran navigation was awesome. And it preceded GPS for you kids out there. And they used Litz wire in a lot of the 100 kilohertz wiring for the very same reason. I don't know how to answer your question, Mr. Tim Beattie, but I think I smell a Nobel Prize in the works. Anyway, so that's skin depth. Now you guys know about it, and you know why your clients are asking you for unreasonable demands on machining and plating and getting the alloys just right, because they care very deeply. And if you mix skin effect with ferri and ferromagnetism, paramagnetism, diamagnetism, and anti-ferromagnetism, you have the formula for complete and total disaster.
The Secretary will disavow any knowledge of your actions. Good luck, Jim.
Well, that's it. Thanks for hanging in there, guys, while I unloaded, and I feel better. This is like nerd therapy for me, and I feel much more relaxed. So I don't see any reason we won't be back next week with some surprises. Mr. Unix Carbide, relax. We're done talking about cucumbers. We are completely done with it. We will randomize your board full of cucumbers on Rusty Nails, and there will be no retained charge. If you guys need something flat or tools to make something flat, head over to PFGstones.com. I'm happy to report that there's 2 orders left in the queue, and I have to make 6s and 4s, and I'm going to have to flip a coin which one I start with. So, Mr. Josh is typing. Any schedule things that I need to get to? Yeah, stick around after the show where we discuss taking the cucumbers and making pickles. In the meantime, get flat and stay flat. We'll see you guys next week. Have fun.